So now, okay, what we saw is like from Planck result. First of all, energy of light seems to depend on the frequency, but also like each frequency can have like multiple photons. That what we are going to call is like, so we are going to call each of these like there is like, for example, there is like a frequency mode h nu, and if n is equal to 1, I'll say that there's like one photon with that frequency. If n is equal to 2, there's like 2 photons with that frequency. If n is equal to 3, I have 3 photons with that frequency, and so on. But typically in a thermal bath, photon can be created and absorbed by the cavity wall, right? There's no law that says like photon number will be conserved. Cavity walls spontaneously emit photons, or they can spontaneously absorb. And inside the, although there is nothing outside, inside the cavity, there's like a thermal equilibrium, and this thermal equilibrium necessitates like a statistical description of this number of photons, and if you do that, you are going to find this distribution, which is the average or expected value of photons at given frequency and given temperature. Hopefully we are also going to derive this result towards the end, but like I said, you have to be patient. Now I want to talk about something called photoelectric effect. Let me, like, without any motivation, let me try to show you the experimental setup. Like I have like here is like a metal, and I can just change the metal whatever I want. I can make it tungsten if I want, I can make it like aluminum, I can make it any metal I want. And I want to connect this metal like a voltage source, and also maybe like this, like a voltage source, so that I can change the applied voltage, and I can also measure the current. However, on the other side, I also put the same metal, but as you can see, there's like a vacuum in between, right? Like there shouldn't be any current under normal conditions, but like typically in real experiments, people also isolate this and put it in a vacuum chamber, so that it's like more like a controllable and reproducible experiment. So what happens is like you send light comes in, and it knocks out, and there are like okay, what is metal? Metal is an object full of electrons, right? By definition. And for something to be metal, electrons should be mobile. And if electrons move, you can actually move it out of metal too, because that's the metal. And electrons out, right? This is E. And as a result, you are going to read a current, right? Light comes in, electron goes in, but flow of electron is a current, so there must be a resulting current. But how much electron is moving? How many electrons do I have? I can, for example, this is like a what we call is retardation potential, right? If you look at the pluses and minuses and try to think about it for a minute, if you increase the potential, that actually applies a force on electrons in the opposite way. By increasing this retardation potential, you can actually stop the current, and from that you can like do the reading like stopping potential. Let me call it V naught, stopping potential. So this is the setup, and of course there is like a frequency of lights. I can send green lights, I can send red lights, I can send yellow lights, I can tune the experiment any way I want. And let's see the key results from this experiment. The first one, is, so let this be, again, intensity, and this is the current, but because the currents comes from like light, we are going to call it photo current. And here, V naught, the stopping potential. Of course, if there is no V, I want to extend this just a little bit. Let me take this a little bit. Of course, if there is no stopping potential, there will be a current, right? And there's like a photocurrent. And as you increase the stopping potential, slowly you reduce the current. And at some point, there's like a threshold. Let me call this threshold. Threshold voltage, at which point there is no current at all. The reading A in the ammeter is 0.
Because of the V threshold is stopping potential.
Yeah, I think maybe I can call this like retardation potential. I think the threshold is the, I don't know what to call it. Like, let me, in my notes, I call this V naught. Let's stick with that. Let's call this V without naught, right? Whenever the current is 0, let's call this V naught. Thank you. So this is some light intensity I. So I can, for example, keep the frequency the same, but I can increase the light, right? Suppose I have one light source, like 2 light sources rather than 1. I double the amount of light I sent and see what happens. What you'll see is the photocurrent will increase, and as you increase the voltage, it's going to decrease. But surprisingly, experiment finds out the stopping potential is exactly the same. So this is, for example, 2I. I increased the intensity twice, but I ended up finding exactly the same stopping potential. And I can increase it even more. Suppose I did 3I, and again, the result is same stopping potentials. Maybe I can just say V naught to be short for all intensities given nu, a frequency nu which we don't care at the moment. So this is experiment 1. So in experiment 2, rather than changing the intensity, right? Intensity is the most logical thing to change, and we would expect that, you know, more light would give more current, which would require more stopping potential. But it seems like more light, more current, but the same stopping potential. Let's see how things change with the frequency. Again, so this be photocurrent. So this is, again, this is current. And this is V, applied voltage. And I apply, like, I don't know, some frequency. And I have some V naught. And if I increase the frequency, like, okay, this is, let me call this, maybe I can, okay, this is V1. Let me increase it a little bit, so V2. With the increased frequency, it seems like I require more stopping potential, right? So this is V naught, so this is V naught prime. And if I decrease the frequency, I have, let me actually sort it out. Let me write it like this. nu1, nu2, nu3, and nu1 is bigger than nu2 is bigger than nu3. And here, like, keep constant intensity, but tune frequency. So that's the second experiment. So we can, like, in the third result, we can do this second experiment a little bit more careful. For example, we can just look at it. Okay, I can draw lines. So this is, let's say, maximum electron energy, which is in electron volts, which is given by stopping potential, right? Look at your stopping potential, multiply it with E electron charge, and that's your maximum energy. And you can look at it as a function of frequency nu. And typically, like, say for cesium, you have a line like this. So this is cesium, and this threshold frequency seems to be 4.5 times 10 to the 4 hertz, or which is equivalent to 1.9 eV. And here, so this is for cesium as the host metal. Rather than cesium, let's say you are using sodium. It's exactly the same but shifted. So this is sodium, and here is 2.3 eV. And for, like, let me give one more example. For calcium, another metal, this is 3.2 eV. Okay. So here, the situation was like that. At the moment, this experiment was a puzzle. Planck's result came up, and actually Planck, for his formula, he thought actually the quantization we saw was on the walls of these vibrators, right? He was thinking about the cavity walls to be vibrators which were emitting light, and those vibrators were quantized in his head. So that if the vibrator is quantized, the light emitted from the vibrator is quantized. But light could be continuous according to Planck. So wall oscillators on cavity wall was quantized. And Einstein, actually light itself was quantized. Einstein said light itself was quantized. Okay? Yes?
For these materials that you do, can you one more time explain, like, the light that you emitted?
Light is not emitted, right? We send the light,
Okay.
light comes in, current comes out. I can change the light source and read what the current does, right?
What was the role of those materials?
So different metals have different properties, right? And let's also talk about that. Also, Einstein modeled the metal like this. So you have a box, right? So this is, say, this side is metal, and this side is vacuum, and inside the metal you fill it up with electrons. So these are electrons, and you need to okay, so this is vacuum. So if you want, this is the energy, and this is E is equal to 0. To free up an electron, you need to take this electron and break it up from the metal. To break it up, Einstein modeled this with something called work function. Okay. And he said this work function, the minimum amount of energy you need to pay to break up an electron is proportional to h times nu minimum, which is what you have here. Right, this is nu minimum. And different metals have different nu minimums. Okay. And suppose you give more energy than the work function, right? You can, like, nobody like tells you to give this nu minimum. You can give more frequency than what this is. Then what is going to happen is kinetic energy of electrons, or maximum kinetic energy, which is what you read with this stopping potential, is equal to the frequency you sent, and from this sent total energy you subtract this work function. So, okay. These are two important formulas due to Einstein. Uh-huh.
This is the representation of conduction band above.
Yes, but let's not make it complicated. Yes, this is like a metal. We don't know anything about conduction band or valence band. This is more like I think at the time Einstein didn't know it either. So there's like some electrons exactly like in a bucket of water, right? If you want to take like a drop of water from the bucket, you have to hold it and kick it out with the energy, otherwise it cannot go out. But I think towards the end we can have these things like conduction band, valence band. Let's not make it it is already very complicated at the moment. Let's not think about those things. Forget what you learned, if you can, please. Okay.
So if you don't mind, can I make a pause for what I related?
Yes, yes.
Thank you.
Okay, so this is equation number 1, equation number 2, and if you combine 1 and 2, what you are going to find is kinetic energy max is equal to h times nu minus nu min, which explains this last, right? Basically, frequency and maximum energy is linear, and the proportionality constant, the slope here, right? You can calculate the slope, is the Planck's constant. You can see slope of experiment number 3. Okay. Now, typically the range for this photoelectric effect takes place typically happens in the visible. And which, like if you look at the visible light, which is like a few hundred nanometers wavelength, you can convert that to energy. It happens to be 1 to 10 eV, which is order of like work function of like metals, a few electron volts.
Can you once more time explain what you define work function?
So the work function is minimum frequency, right? The minimum frequency you need to like use to break at least one electron. Any frequency below that is not going to give any photocurrent, no matter how much light you send. So the conclusion of this whole exercise, let's conclusion. So light, first, light is a wave. There's no problem with that because of like interference, right? Young double slit experiment. And it also gives diffraction, which is like a wave phenomena. But also, light is a particle. Why? Because E is equal to n times h nu. It comes like a little packages of energy as in particles. But also, it knocks out electrons exactly like exactly like two billiard balls collide. Light can collide with your electron and knock it out. It can give it a momentum, right? Light is a particle, and this is supported by Blake body radiation and also photoelectric effect. Now, if it's a particle, we have to go back and think about our interference experiment. Right? I can send particles one at a time, right? Particles are not like waves that penetrate in space. There's like a one particle, two particle, three particle. Suppose I have this double slit experiment. Here's two slits. Typically, we think about sending waves like this wavefront. It could be water waves, but it could also be like a plane wave, light. But now we are saying that light is a particle. Suppose we put that particle and there's like, I don't know, some fancy quantization inside this particle. And particle is, there's only one particle, right? Today, the technology enables us to create photon resource, which is like created one at a time. So you can go and buy these fancy instruments which shoot one photon at a time, right? There's only one photon. So this one photon at a time. Now there are two questions. Then let me call this slit A and slit B, which I want you to think about. I'm not going to tell you the answer. And there's like if you want screen, here is a screen. So the question number one, do we still get interference if we send one photon at a time, right? Do we still need to get interference? Anybody want to have any comments on that? If I send one photon at a time, typically interference, what we say is like there's like light coming from here, and they combine here, right? But if I send only one light, this guy goes through here or here, right? How, like, where is the other to combine and create the interference? So this is one question. And the second question is related to this one. Does the light pass through A, slit A or B, right? I have to choose one or the other, right? This is a particle. I can't just say like, oh, it's like a wave, a front that's running soldiers next to each other. Some go through A, some go through B. We can say that. It has to go through A or B. And which one? Good. Any questions? Any suggestions?
Why don't you give answers?
Because I mean, if you care, you can think about it, go and search. Sometimes if you have like a very nice argument and I give you the ready-made meal, I think there's no value in that. I think this is one of the exciting things about quantum mechanics that happened recently. Yes.
When you put one particle at a time, what does that mean? Like at the time is 1 second?
Like I sent, like I have my operators. I sent one photon, and I wait. Okay, I sent one photon today, and in the screen, I see the photon hits here, and I don't do anything else all day. Okay, the next day I want to make sure my instrument just slows down, all the photons in the media just disappeared, whatever. The next day I come here and I send one more photon. I don't know, it hits here, something like that. And I do this like over a year, and I collect the result. And the question is, am I supposed to see the interference pattern? And if your answer is yes, who is interfering with who? I'm just sending one person at a time. I thought I was supposed to have two photons combined to have an interference. So this is like the second question. And the third question is, if this is just one photon, it should go either from A or B. Which one? Or like what? How do you reconcile all of these puzzling aspects? So the message here is, it's easy to say light is a particle and end of story, but it's really hard to convince somebody about this like result. Any questions or comments?
How do you define a photon?
Like a photon is like for a given frequency, right? There's like only one photon, right? There's only not two, not three. There's one only. So can I continue, or any discussions, or any? Yes.
There is only one photon. Isn't the direction you're sending it in important then? Because it's only one.
Yeah, typically like in the there's like you have to think about this logistics, but I think I'd like to like consider this experiment in our like earlier philosophy. Like think about this like a Gedanken experiment. Of course, a real experiment which was actually done recently, and if you look at the Nobel Prize from 2 years ago, you can read about these people. I think I have to think about all this, like which direction, how do I send it, how do I devise like a double slit, right? And those are like tough questions. A good experimental physicist should know. But for the moment, we don't care about these logistic details. Yes?
John, we know speed of light, so would uncertainty and Heisenberg's principle?
We don't know our uncertainty rate, but we are going to come to that. Like I think for the moment, I think just think about this like a classical phenomena. Yes?
Can we not measure the time that has been passed throughout this motion?
Yes, you can measure time with your clock, yes.
How much time would be passed in that case?
Like I made like a cartoon of time, right? Like I sent one photon, right? There's like, I go to like Amazon.com, I order one of those devices that sends me one photon at a time, and I also order like a double slit, and I put the double slit, I put the device, there's like a button. Today I press the button, and on the screen I see like a light. The next day I do the same thing again.
But depending on the trajectory of the photon, doesn't the place that we see it on the screen change? And by measuring the time, since the speed of light is constant,
By measuring the time,
yeah,
after I press the button,
because total distance changes if we see on top, for example,
uh-huh.
the screen.
Total distance to reach the screen,
Well, the distance that
right?
the photon has taken.
Right? Like you are saying that the distance here is different from the distance there, so there will be different times for them to, or does it? That's exactly what I want you to think about. So this is like a classical intuition, which actually does not work in quantum world. Like suppose you know the time, right? It goes through, I don't know, 10 to the minus 20 nanometers, nanoseconds or something like that. So, I mean, I don't know the time, but is it going to resolve our issue here? This is question number 1 and question number 2. Okay. So I have a little bit more material, but if you feel tired, we can stop here and continue next time. But if you want to hear more, we can talk about X-rays for maybe like 15 more minutes. How many people want to go on? How many people want to finish? Okay, let's finish it here. I'll see you guys next time.